Well, good morning, everybody. I'm very happy to be here in Stockholm. What I'm going to tell you is based on a work with David, who is here, with Enrico and Patfa. Well, this is a brief overview of my talk. I'll briefly recall what inflation and the related observations are. I'll briefly recall what Galilean genesis is as an alternative model to inflation, and then we'll go through the essential topic of the talk based on extended Galilean genesis, and we will briefly discuss about stability as from an effective theory point of view, and at the end we will draw the conclusions. Well, as everybody knows, the standard Big Bang model suffers from some problems. The horizon one, the flatness, and that one linked to the generation of density perturbations as seeds for the universe large-scale structure formation, and observe an almost scale invariant adiabatic and Gaussian spectrum for density perturbation. And the inflation represents a possible solution to all these problems with the so-called strong energy condition violation. So what about spectra? As everybody knows, these are the standard expressions for the scalar spectrum, the tensor spectrum. And let me observe that the scalar spectrum is sensitive to many details, and in this sense it is model dependent, or in other words, we can play, if you want, with the potential shape or the speed of propagation or the speed of sound in order to reproduce what we really observe, while the tensor spectrum, which fixes without ambiguity the energy scale of inflation, is much more model independent and robust with respect to the scalar spectrum. And given this robustness, I want to address the problem of having a positive tensor tilt. As everybody knows, the standard Zlorod scenario predicts the negative NT. So it is interesting to ask this kind of question. And the second one is, which is obviously related to the first one, is it possible to build a null energy condition violating a stable quantum robust evolutionary cosmological theory? In this sense, as you know, this is the standard picture of the G-inflation paper, which represents the phase space of the theory. The horizontal line is the h equal to constant curve, which divides an upper region with an decreasing h and a lower region with an increasing h. So usually what we have in mind is that the lower region with an increasing alpha rate suffers from instabilities in the form, for example, of a negative speed of sound. But what I want to show you is the possibility of completing, in some sense, the lower part of the picture in order to build a stable cosmological scenario without classical instabilities of this kind. So let's briefly recall what Galilean genesis is as an example of violation of the so-called null energy condition. So it's based on conformal symmetry of the flat space version of the theory, spontaneously broken down to the de Sitter group. The quasi-Minkowski nature of the space-time of the theory naturally solves the problems connected to flatness, homogeneity, and horizon, and the unbroken dilatation invariance naturally implies a scale invariant spectrum for density perturbations. While, nevertheless, this theory cannot predict sizable effects for the tensor spectrum. In other words, if you want, you can imagine that the gravitational waves are sensitive to what the real metric is doing, but at the beginning we have a Minkowski space-time, so the tensor spectrum is very blue and very suppressed. So this is the theory, very briefly, ties our scalar field. This theory admits a solution in Minkowski of this form, which spontaneously breaks the conformal group down to the de Sitter group. And the dilatation invariance of the theory naturally implies a zero energy density, while we have a negative pressure, meaning that we have a strong violation of the null energy condition. So obviously the fact that we have a non-zero stress energy tensor means that represents a source for the gravitational field. So we expect that the previous solution would not be a solution anymore sooner or later. In fact, if we introduce gravity, we can, with the standard metric, we can use the Friedman equation, and we can estimate the Hubble shape at the early times, and also we can estimate the time at which our effective field theory approach doesn't apply anymore. So we have our effective field theory breaks down, and at the time we impose Wheating processes. So this is just a sketch of what is happening. The green curve is the standard slow road inflation with a decreasing h, let me say with a singularity at the beginning, while the orange curve represents the Galilean genesis scenario. You see that we start from a Minkowski space-time, and at one point we are exiting the regime, the consistent regime of the theory. And so, summarizing, we can say that in this scenario, we do not have the Big Bang at the early times, no energy density, so the energy and the Hubble rate get created from the null energy condition sector, but we cannot have, as I said, gravitational waves in the sense that we are starting from a Minkowski space-time. So the idea is to modify this picture in order to, if you want to extend this orange curve, in order to make this consistent without this problem from an effective field theory point of view, but also using all the interesting features of this theory. So the idea is the following. So we would like to have a sort of this blue curve interpolating two asymptotic regimes, and the general idea is this one. Consider theories with asymptotic enhanced symmetries. So the role of the symmetries is very crucial in the sense that we know that the solutions at the early time and late times are natural attractors, and the symmetries guarantee the radiative stability and the quantum robustness of the theory. So we have a full control, at least over the asymptotic stages. For example, we can have a scale invariance at early times and shift symmetry at late times. And for example, this is a simple example of a theory which could in principle interpolate between these two asymptotic regimes. And very briefly, this is the numerical result. It's not important to go through the details, but you see, we can. This is the expected shape of the Hubble rate I've shown you before in the sketch. We have just a problem related to the speed of sounds, which displays a gradient instability, at least for the numerical study we were able to do. But let me say that obviously this is not a so dangerous problem in the sense that we can modify our theory in incorporating higher order effects in order to cure this classical instability. But anyway, we can forget about this because I want to show you the possibility of going beyond the limitedness of these two simple examples using a more general approach and an analytic approach to the problem. So, let's discuss a stable version of extended genesis, and the idea is the following. Consider this action with, which is a modified version of the standard Galilean genesis theory. We have two arbitrary, in principle, two arbitrary functions of the scalar field pi. We can use the standard approach, solving the Einstein equations, and now the strategy is the following. So the idea is to find f1 and f2 as only functions of the scalar field. So we can, obviously, we would like to have a particular shape of the Hubble rate as before, as I've shown you before, like this, for example. So we postulate background profiles for the Hubble rate and the scalar field. We find the time-dependent functions f1 and f2 using the previous relations. We can obviously invert the expressions for pi and plug it back into the f1 and f2 in order to find them as functions of only the scalar field.
Excuse me, but
yeah.
These breaks go from symmetry, right? Yeah. These breaks is this choice of f1.
This choice of f1, yeah, it depends. Yeah, it depends on f1 and f2.
Yes. So for the profiles that we'll be interested in, you see that at early times actually the formal symmetry is restored. So f1 and f2 are such that they exactly restore. Yeah. And in late times they are constant.
Yeah.
So you
I mean, you break.
But in the intermediate regime, you do break.
Yeah, because my worry is whether it is stable, this kind of.
Yeah. So you don't have control over the whole history, but at least asymptotically you know that there are enhanced symmetry, and it's natural to expect that you have a solution which interpolates. But you are right. In the middle, there is an extra symmetry actually in the middle, but like Galileans.
Yeah. As I said before, we have the full control over the asymptotic regimes, but we cannot infer a lot about the intermediate stage, even if that is saying we can say something about an approximate symmetry. But anyway, yeah, the asymptotic regimes are okay. So, obviously motivated by the genesis solution, we assume this kind of shapes, and if we go through the analysis, we can make the following observations. Obviously, Galilean genesis is recovered for a particular choice of this parameter, lambda, beta, and T star. We cannot avoid a gradient instability if lambda is equal to 0. But if lambda is different from 0, the system can evolve from the Sitter space without any instability, so without classical instability. And at the end, at late times, our scalar field acquires a linear profile. So, very briefly, what about the stability? We can use the standard approach using an effective theory point of view. We can use the unitary gauge, using also alien variables. This is the action in this gauge. We use the standard decomposition, the standard metric, and we can write down the quadratic action for the scalar perturbation. And our theory predicts that A and B are strictly positive. So we do not have the gradient, or we do not have ghosts in our theory. So we are sure about the classical stability of the theory from the effective theory point of view for perturbations. So I think we can conclude, and this is the summary. So the idea is to propose a model which is obviously an extended version of Galilean genesis, but prefer an early time complete realization of inflation, in the sense that I've shown you. This theory predicts a positive tensor T, the tensor spectral index for the tensor modes. We have a strong violation of the null energy condition at intermediate times, and as I show you in the previous sketches, the universe can emerge from an almost enclosed space-time in a stable manner, so we do not have any singularity at the beginning. We do not have also classical instability during the late evolution, which can interpolate between quasi-enclosed space-time and a de Sitter regime at late times. Then let me again emphasize the fact that the asymptotic evolution is under a full control from also a quantum point of view. I didn't have time to show you how, but this is the case. And also I didn't have the time, but we can also show that the late time inflationary dynamics can produce a lab tensor to scalaration, and also sizable effects for non-Gaussianities. So this is our picture, and that's all.